So I'm Philip Edmondson. I'm a staff scientist here at Oak Ridge National Lab. My role here is to do a lot of characterization of nuclear materials, in particular using the CNMS local electrode atom probe. So the atom probe works by taking a needle-shaped specimen and applying a high voltage to it, which you then pulse. Alternatively, you can also use a laser. And what that does is it causes field evaporation of the surface atoms, which then get extracted and go through a time-of-flight detector onto a position-sensitive detector. So the time-of-flight spectrometer gives us our chemical information, where the position-sensitive detector gives us our XY position of where the atom was. And then using an algorithm, a back projection algorithm, we can then build up a three-dimensional image of the specimen as it was. And from that information we have the spatial position, in X, Y and Z, and we also have the chemical information. So we can build up a very detailed representation of what the specimen was, and from that we can see things like the precipitation, clustering, interfacial segregation and depletion. In particular we look at a lot of nuclear materials, so a lot of steels for nuclear reactors. We look at cladding materials of nuclear fuel, so the zirconium alloys. In particular there we're looking at oxide formation, interfaces, etc. We also do a lot of work in the fusion materials work, so we look at a lot of tungsten materials, looking at how radiation affects tungsten, in particular how transmutation products form clusters, which turn the tungsten even more brittle than it is in standard conditions. The strength of the atom probe is that we really have very high resolution, high fidelity data that comes off this, and it's in 3 dimensions. So whereas TEM can give us a lot of information, it's typically only in 2 dimensions. This gives us a 3rd dimension. So it really does help us look at things like precipitates and segregations to grain boundaries, where we can get profiles of how the elements within the material actually behave, and then we can do that for different conditions and get a bigger picture of what's going on. And then because it's almost atomic scale, we can give that feedback into modelers who can then scale up the problem. The issue with the atom probe is that we look at very, very small volumes of material, typically 100 nanometers by 100 nanometers, so very small volumes. So we need to do a lot of experiments to get an overall bigger picture of what's happening on that kind of micro scale, and then we can feed that into other people, so modelers for example, or TEM or SEM, and then get the bigger picture. So we can actually, although we're looking at nanoscale, we can actually build up to the macro scale in how a material is behaving under radiation conditions.